On May 12, 2022, humanity looked at the center of the Milky Way for the first time. Not metaphorically, not approximately, directly. The Event Horizon Telescope, a network of 8 radio observatories spread across 4 continents linked together to form a single instrument the size of the Earth, pointed at the object 4 million times the mass of the Sun, sitting at the heart of our galaxy, and took a photograph. The image showed a dark center surrounded by a bright glowing ring of superheated gas. It was exactly what the equations predicted. It was exactly what decades of theoretical physics said a supermassive black hole should look like when photographed with sufficient resolution. Scientists called it one of the greatest achievements in observational astronomy. The team behind it received widespread recognition. The question of what sits at the center of the Milky Way appeared to have been answered definitively. On February 5, 2026, a team of researchers published a paper in the monthly notices of the Royal Astronomical Society, suggesting that everything we photographed that day may have a completely different explanation. The object at the center of our galaxy, the thing we have been calling Sagittarius A for decades, the thing we have been pointing at as the definitive proof that supermassive black holes anchor large galaxies, may not be a black hole at all. It may be dark matter, and the most unsettling part of this story is not the claim itself. It is the fact that with every instrument currently available to us, we cannot tell the difference. To understand why this matters, you first need to understand what we thought we knew and why we were so confident. The center of the Milky Way has been one of the most studied regions of the sky for decades. Long before the Event Horizon Telescope image, astronomers had been watching a group of stars called the S stars, a small population of massive young stars racing around the galactic center at extraordinary speeds. The most important of these is a star called S2. Its orbit has been tracked for over 30 years with increasing precision. S2 completes one full orbit of the galactic center every 16 years, and it does so at speeds reaching several thousand kilometers per second, approaching 1/10 of the speed of light at its closest pass. The only object that could produce those orbital speeds at that orbital distance is something with a mass of approximately 4 million solar masses concentrated in a region smaller than our solar system, a region of space so compact that if you tried to fit the same mass into that volume using any known form of ordinary matter, it would collapse. The density implied by those numbers has only one conventional explanation: a singularity. A point of infinite density from which not even light can escape, a black hole. For decades, the standard interpretation was exactly that. There is a supermassive black hole at the center of the Milky Way. The S stars are orbiting it. Their orbital speeds and trajectories trace the gravitational potential of the central mass with extraordinary precision. And then, in 2022, the Event Horizon Telescope collaboration provided what appeared to be the definitive visual confirmation: the image of a dark shadow surrounded by a bright ring of glowing gas, exactly the shape that general relativity predicts for the region immediately surrounding a supermassive black hole. The case appeared closed. The new research reopens it. Led by Valentina Crespi of the Institute of Astrophysics La Plata in Argentina, an international team asked a question that sounds almost impossible to take seriously on first encounter. What if the object producing those orbital speeds is not a black hole at all? What if it is something else, something that has the same mass, occupies a similarly compact region of space, bends light and warps space-time in a way that is observationally indistinguishable from a black hole with every instrument we currently possess? The answer they found was fermionic dark matter. But before we get to what fermionic dark matter is and why it could mimic a black hole so perfectly, we need to spend a moment on dark matter itself. Because the concept of dark matter sits at the foundation of this entire story, and it is worth understanding precisely what it is not, and why its presence at the center of the Milky Way would be one of the most significant discoveries in the history of astronomy. Dark matter is one of the most significant unsolved problems in modern physics. We know it exists. This is not a guess. This is not a placeholder for ignorance. The gravitational effects of dark matter have been measured with extraordinary precision across dozens of independent observational methods. From the rotation curves of individual galaxies to the large-scale structure of the cosmic web, to the detailed pattern of temperature fluctuations in the cosmic microwave background. Every one of these measurements points to the same conclusion. There is approximately 5 times more gravitating mass in the universe than can be accounted for by all the ordinary matter we can see, detect, or measure. The missing mass is dark matter. It makes up approximately 27% of the total matter and energy content of the universe. Its gravitational influence is responsible for how galaxies hold together, how they cluster into groups and superclusters, how the filaments of the cosmic web assembled from the smooth plasma of the early universe into the structured architecture we observe today. What we do not know is what dark matter actually is. It does not emit light. It does not absorb light. It does not interact with ordinary matter through electromagnetism, the force responsible for almost every interaction we experience in daily life. It does not interact through the strong nuclear force that holds atomic nuclei together. It responds only to gravity. We have never detected a single dark matter particle in a laboratory. This is the substance the new research is proposing may sit at the center of our galaxy. One theoretical candidate for dark matter is a class of particles called fermions. Fermions are particles that obey a specific quantum mechanical rule called the Pauli exclusion principle, the same rule that governs electrons, protons, and neutrons. The Pauli exclusion principle states that no 2 identical fermions can occupy exactly the same quantum state simultaneously. In practice, this means that fermions resist being compressed together beyond a certain density. This quantum pressure is what holds white dwarf stars and neutron stars together against the crushing force of their own gravity. In a white dwarf, it is the quantum pressure of electrons resisting compression that prevents the star from collapsing into a black hole. Fermionic dark matter works on the same principle. If dark matter is made of fermions, then a sufficiently dense concentration of dark matter particles would resist gravitational collapse through the same quantum pressure mechanism. It would reach a stable configuration, a compact, dense, gravitationally stable object that neither collapses into a singularity nor disperses into the surrounding space. The result would be something analogous to a dark matter neutron star. The question Crespi and her colleagues asked was whether a fermionic dark matter core of the right mass and density could reproduce every observation we have attributed to Sagittarius A star, the orbital behavior of the S stars, the specific shape and size of the Event Horizon Telescope shadow, the rotation of the galaxy as a whole. The answer they found was yes. The numbers work in a way that is deeply unsettling. The team modeled the orbital behavior of S2, the star whose 16-year orbit around the galactic center has been tracked with the greatest precision of any S star. They ran the simulation under both interpretations, the conventional 4 million solar mass supermassive black hole and a fermionic dark matter core of equivalent mass and appropriate density. Both models reproduced S2's observed orbit with near identical accuracy. This is not a minor technical quibble about fitting parameters. This is a fundamental ambiguity in what the most precisely measured orbit in the history of galactic astronomy is actually telling us. 30 years of careful observation, hundreds of individual position measurements, a Nobel Prize awarded for the work, and the data cannot distinguish between a black hole and a dense clump of dark matter. The shadow is equally ambiguous. In 2024, a study by Pell and colleagues demonstrated mathematically that when an accretion disk of hot infalling gas surrounds a dense fermionic dark matter core, the core bends light through its gravitational field so powerfully that it casts a dark shadow surrounded by a bright ring. The specific size and shape of that shadow is consistent with the image taken by the Event Horizon Telescope in 2022. Lead author Valentina Crespi stated the implication directly. The dense dark matter core can mimic the shadow because it bends light so strongly, creating a central darkness surrounded by a bright ring. Carlos Arguez, one of the paper's co-authors, went further. If you were to travel toward the center of the Milky Way in a spacecraft, approaching the object we have been calling Sagittarius, a black hole would destroy you long before you reached its center. The tidal forces at the event horizon of a 4 million solar mass black hole would stretch and compress you into a stream of particles. A fermionic dark matter core would not. You could fly directly through it. The gravitational field would be intense, but there would be no event horizon, no point of no return, no singularity. The most dangerous object in the galaxy, the thing anchoring 400 billion stars in their orbits, might be something you could pass through without being destroyed. But the most compelling aspect of the new research is not what it says about the center of the galaxy in isolation. It is what it says about the entire galaxy simultaneously. One of the long-standing puzzles in Milky Way dynamics is the precise shape of its rotation curve. A rotation curve is simply a plot of how fast stars and gas orbit the galactic center at different distances from it. In a solar system, the rotation curve follows a predictable pattern called Keplerian decline. Objects farther from the central mass orbit more slowly, the same way Neptune orbits the Sun far more slowly than Mercury does. But the Gaia DR3 data, the most precise map of the Milky Way's rotation ever assembled, tracking the positions and motions of billions of stars, revealed something unexpected at very large distances from the galactic center. The rotation curve is not flat all the way to the outer edge of the galaxy. It shows a Keplerian decline, a fall-off in orbital speeds at the galaxy's outermost regions. This is difficult for standard cold dark matter models to reproduce. The fermionic dark matter model produces a more compact halo with tighter outer edges. Its predicted rotation curve at large radii falls off more steeply than cold dark matter, more consistent with the Keplerian decline observed in the Gaia data. The same model that reproduces the orbital behavior of the S-stars at the galactic center and the shadow of the Event Horizon Telescope image also reproduces the rotation curve of the outermost stars in the Milky Way. This is the key claim. Not just that the galactic center could be dark matter instead of a black hole, but that the same continuous dark matter structure, described by a single unified model, explains both the behavior of stars racing around the core at near relativistic speeds and the behavior of stars orbiting quietly in the galaxy's outermost halo billions of times farther away. Arguez described this as the first time a dark matter model has successfully bridged these vastly different scales, including modern rotation curve and central stars data, simultaneously. The supermassive central object and the galaxy's dark matter halo are not two separate things. They are two manifestations of the same continuous substance. If this is correct, the Milky Way is not organized around a black hole. It is organized around a single unified dark matter entity that is simultaneously the dense compact core at the galactic center and the vast diffuse halo surrounding the entire galaxy. The black hole and the halo are the same thing. And the most powerful gravitational object in our galaxy and the invisible substance that holds its outer reaches together are a single connected structure. Here is where the story becomes genuinely uncomfortable. We took a photograph in 2022. We called it the first image of the black hole at the center of the Milky Way. We taught it as a confirmation of general relativity, a validation of 30 years of stellar orbit tracking, and a triumph of international scientific collaboration. Hundreds of millions of people saw that image. It appeared on the front pages of newspapers in every country. It was one of the most widely shared scientific images in history. The new research does not say the photograph is wrong. The shadow is real. The ring is real. The mass producing both of them is real. What the research says is that the photograph may be showing us something we did not intend to photograph. That the object producing the shadow and the ring and the orbital velocities of the S stars is not the object we assumed it was when we pointed our telescopes at it. Shep Doeleman, the founding director of the Event Horizon Telescope project, offered a specific challenge to the new interpretation. The observed spiral pattern of magnetic fields near the galactic center appears particularly consistent with the properties of a black hole rather than a dark matter core. Magnetic field behavior near a black hole is governed by the accretion dynamics of infalling gas in the presence of an event horizon. Dark matter core with no event horizon might produce a different magnetic field structure. This is a legitimate scientific objection. The debate is not settled, but neither is the consensus as unassailable as it appeared on May 13, 2022. The question of how to resolve the ambiguity is where the next decade of research will focus. The Event Horizon Telescope is being upgraded. The next generation. Event Horizon Telescope, incorporating additional observatories and improved receiver technology, will provide resolution improvements that may reveal subtle differences in the structure of the shadow or the behavior of gas, orbiting the central object on timescales of hours and days. The Very Large Telescope at the European Southern Observatory has been tracking the orbits of the S stars continuously for over 3 decades and will continue doing so with increasing precision. Future measurements may detect subtle deviations from the orbital predictions of each model at levels that current instruments cannot resolve. There is also a theoretical prediction from the fermionic dark matter model that provides a potential observational test. The model predicts that fermionic dark matter cores cannot exceed approximately 10 million solar masses before the quantum pressure stabilizing them is overcome by gravity and they collapse into a conventional black hole. Sagittarius. A star at 4 million solar masses sits comfortably within that limit. But the supermassive black holes at the centers of larger galaxies, with masses of hundreds of millions or billions of solar masses, would already have exceeded the fermionic limit and collapsed. For now, the photograph we took in 2022 remains what it was when we took it. An image of the most massive compact object at the center of our galaxy, a dark center surrounded by a bright ring. An object 4 million times the mass of the Sun doing something to the fabric of space-time that no other object in our cosmic neighborhood comes close to doing. Just are not certain anymore what that object actually is. There is something worth sitting with at the end of this story. The supermassive black hole at the center of the Milky Way was the one feature of our galaxy we considered definitively confirmed. Every other mystery about the galaxy, the nature of dark matter, the origin of the central stellar population, the mechanism driving the Fermi bubbles extending above and below the galactic plane, all of them were open questions. But Sagittarius, a star itself, was settled. The Nobel Prize had been awarded for the work establishing it. The Event Horizon Telescope had photographed it. The textbooks had been written. February 5th, 2026 did not undo that work. The orbits are real. The shadow is real. The mass is real. The physics that produced those observations is not wrong. But physics gave us something new. A model in which everything we measured is equally consistent with a different object entirely. If that model is correct, then every star in the Milky Way, including our Sun, 400 billion stars in total, is not orbiting a black hole. It is orbiting dark matter, which means if it is dark matter, we have not answered the question of what sits at the heart of our galaxy. We have just discovered that the answer is stranger than we thought. Good night.